heard the saying, the dose makes the poison. Well, the biochemical equivalent is kind of like the concentration makes the binder. So what do I mean? Basically, everything in biochemistry in, requires that molecules are like coming together and doing stuff. So they have to come together and then like stick long enough for something to happen if it's like an enzyme catalyzed reaction or something, or just stick, um, like structural things. But if you have a ton of one of the things, it's gonna seem like it's gonna stick, it's gonna bind because it just keeps revving up, and every time it comes off, there's something there. So when we talk about whether something binds or doesn't bind, that's really not a, it's really not a binary thing like that. You don't have things that bind and things that don't bind. Basically, it's all like a continuum. So the if you crank a ton of one thing, even if they're not good binders, then they're still going to be like, they'll still bind. So when we talk about affinity, that's like how strong that binding is. And that can be either because it has a high like on rate. So if they happen to stick, if they happen to like collide, then they're more likely to stick. Or like a K off, so that's like the off rate. So if you have a lower K off, if it gets stuck, it'll stay stuck. Whereas like with the K on, it's referring to like how easily it can actually get stuck initially, but not like how fast is falling off type of thing. But basically, so you have that K on and K off, and these are these opposing forces, like on and off, these opposing things. But then overall, if you have a ton of the stuff, even if it's having a trouble sticking, or even if it's falling off quickly, it still can bind. And so when we talk about binding affinity, we often use this term called KD, and that refers to the concentration at which half of a molecule will be bound. So you can think of, if there's a ton of it, then it will like all be bound. And then if there's not any, then none will be bound. And so you can measure across the spectrum and get this idea, this KD, which is the halfway point. So if you have two things that really like each other, they have a high affinity, then what's going to happen is you don't need as much for them to all be bound. Whereas if you have something that has a low affinity, so they don't like each other, then you're going to have a lot more to be bound. And so we have this value called this KD, which is the half the amount of the binding partner that you need for half of the partner to be bound. So if you, what gets confusing is that we talk about having a lower affinity as having a higher KD, and having a higher affinity as having a lower KD. But you can remember that this is because that's the amount that you need. So how stuffable do you have to be so that it compensates for that lack of affinity? So you can think of concentration as kind of being what kids being able to like compensate for a lack of affinity. But if you have a high affinity, you don't need that concentration boost. So you can actually have binding at a lower concentration. So we often represent KD in like this logarithmic form. So you'll see it like this, and you'll see that something with a lower affinity is going to have a higher KD, and something with a higher affinity is going to have a lower KD. So this gets kind of confusing, but because like higher, lower values. So if you're not used to talking about like KD and stuff, it can be really confusing. But the reason why we have it like this is because it's actually the inverse of the affinity constant, so Ka. And so Ka is in inconvenient units, so it's like 1 over molarity or whatever. And so whereas Kd is in molarity, which is the concentration unit. It's like the number of molecules per thingamabob. I have a post on that. I just don't want to get into it here. I do know what it is. But anyway, yeah, so the KD, because it's like in units of concentration instead of 1 over concentration, then we can more easily like talk about things and compare things and that sort of thing. In addition to depending on the concentration, these interactions are also going to depend a lot on the salt concentration. So one of the things that drives biochemists crazy a lot is that people will say like, that things bind or whatever, but they'll be at really low salt concentrations, or they'll do um, like a pull down experiment where they take cells and they immunoprecipitate something out. So they grab onto one thing and then pull it down, and then so they pull. What that means that pull down is they have like beads or something with like an antibody that'll bind specifically to that um, thing that they're interested in, and then they'll wash everything else off. And depending on how stringent, in order to get like really tight binders, you want to make sure that they have like a high salt concentration. So why is this? Why does high salt um, like interfere with these interactions or whatever? So basically, the higher the salt concentration, the more likely that your stuff is, or the lower the salt concentration, the more likely that something's going to bind, even if they're not really strong binders. So you'll detect weaker interactions. And the reason why this is that you can think of it kind of as the salt acting as like a competitor. So we talked yesterday about how really at the heart of all molecular like attractions is charge. And if you have, we'll go just I'll review in a second, but if you have a salt, it's like creating this charge fog, and the charge of the salt is actually, so a salt um, is something that has a positive charge and a negative charge part. You have a mix of the two. So when you dissolve it, then you have these dissociate, so they come apart. So like you have, so if you put sodium chloride in, you get sodium ion and chloride ion. And so you have a positively charged thing and a negatively charged thing, and they can surround the binding partners and hide their positively and negatively charged regions. And then so you have this high ionic strength, which is kind of like a measure of like the fogginess or whatever. So the higher the ionic strength, the weaker the charge-based interactions are going to be. As we talked about yesterday, this charge interactions are like fundamental to how molecules interact, even molecules that aren't fully charged, because you can have this polarity, this like separation of the um, electron density. So we talked yesterday about electrons being like the negatively charged parts of atoms being like hanging out in these clouds. And they can like kind of shift around in there. So if they shift around one way, then you have a negative charge and a positive charge, even if the molecule overall is neutral. And this allows you to have these like attractions, which can be, so with ion, it's like a full charge. We also have these partial charges, and you can induce like one thing that's charged can induce a shift in the electrons of this thing next to it if it's like coming near. And then these, because opposite charges or like charges repel, so if the electrons come this way, then the electrons over here are going to, and you can have like this these like induced dipoles, as well as some molecules having like permanent dipoles. And so by dipoles, it's like a separation of the charge. So like water, the oxygen is really electronegative. So the electrons really like to hang out over there. So when you have this cloud of electrons, they're going to be found more often by the oxygen. And then the hydrogens are left with fewer than they would normally have. And so then they have this partial negative charge, which is why we say that water is polar. So you have this dipole. Um, and so you can get these interactions in a number of different ways, like, and even something that's not, doesn't look like it's charged, like there's no way that this could have charge or whatever. When you have something charged come near it, you can get this thing called like a London force or a van der Waals interaction or dispersion force, or basically just like, I'm sorry, this isn't what I meant to show, but basically you can have just like random instantaneous dipoles form because those electrons are moving all around. The cloud, we can describe like regions where the electrons are most likely to be in like orbital models, but the electrons are really just like moving all around and doing their own business. And so we're just, if they just all happen to be over in one area, then you're going to get an instantaneous like um random um dipole, and then that can induce a dipole and the thing next to it and that sort of thing. And so these sort of interactions um can occur. So basically the thing to remember is that like, so all basically all interactions are somehow involve the charge, like charge interactions or attractions or whatever. So they might be really small, they might be partial, but these are all like charge based at some level. And so then if you think about having a high salt concentration, you're going to be fogging all of those reactions. And therefore it's going to make it harder. You're going to have a higher affinity between those two things in order for things to stick, or you're going to need a higher concentration of those things. But when you have a bunch of salt, you're kind of like lowering the concentration of those things, the like effective concentration of them, because you're fogging them out, you're hiding them from the binding partners. So those are a couple of ways that you can think about the effects of salt on binding. But the key thing to remember is that the lower the salt, the more likely things are going to bind. So if you want to really make sure that you're getting like specific binding instead of non-specific binding, then you have to like do it at a higher salt concentration, because the specific binding, they're not, because you'll get non-specific binding at lower concentrations, because remember, it's all about like the concentration that matters. So the concentration of the thing, because if you have a ton of it, every time you fall off, you're going to find something to bind back to. And so it'll always seem like you're being bound. There are a few terms that we use to describe binding interactions. So we often call the binding partners a ligand or a receptor. And if something has like one site, we call it like monovalent. And if it has multiple sites, we can call it like multivalent, multiple binding sites, whatever. And so these multiple binding sites allow for like avidity. So when we talk about concentration, so in a cell, you might not have a high enough concentration that you would think that things would actually bind. And it's kind of incredible sometimes that they do bind. But there are a couple of reasons why things bind. And one of them is like an increase in the local concentration of something. So if you locally increase the amount of molecules that are there, then you'll have a higher chance of them actually binding and staying bound. And so one way that you can do this is by having like scaffolding proteins. So like a big flexible protein that kind of binds a bunch of things and holds them close together. And this is really important for like kind of like chain reactions, not really chain reactions, but when you have like a pathway, like often like a signaling pathway or something. So something happens in one place and then blah, 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 blah. Also important for like biosynthesis pathways. But another way you can increase the concentration locally is if, even in concert with those, is if you have like something that's multivalent. And you can have cooperative binding and this effect called like avidity. So affinity is how strongly a single thing will bind. Avidity is, with a V, is like this effect that you, this extra effect you get if you have multiple sites. And because this is what's happening is you have, so if you have like a floppy thing that can bind multiple things, then if you have multiple of them bind together and then they bind to a surface, if one of them binds, then you have an increased local concentration of them around there because you already have them like kind of tethered down on this one. So if a second one binds, well, it's more likely to bind because you have a higher concentration, and if it comes off, it's like not going to float away. So you get these added effects with avidity. And you can say like cooperativity. And so like if binding of like one increases the chance of binding on the other and that sort of thing. And so yeah, so affinity refers to the strength of a single site interaction, and avidity refers to like that added benefit that you get from having that multivalency.